Hello everyone, welcome to the Scalable Big Data Modeling session. My name is Jayesh Patel and I'll be presenting on best practices for scalable big data modeling. After spending over 15 years in building data-driven processes for numerous industries, I thought of transcribing the best practices to model big data, and I'll be presenting them today. Here's the outline of today's session. I'll start with data modeling overview, followed by various data modeling techniques. I'll briefly describe traditional data modeling challenges. In the second half, I will present the key points for scalable big data modeling. Data modeling process. Let's understand it using an analogy. In a library, all the books are classified and arranged on bookshelves to ensure each book is easily accessible. Similarly, when we have massive amount of data, we need a system to organize it. This process of sorting and storing data is called data modeling. A data model is a method by which we organize and store data. Business users consume data insights through the channel of data models. Therefore, data models are the gateway for insights servings to internal and external customers. To draft a data model, we usually start with a conceptual model depicting business context, its value, and various concepts. The logical model defines the data structure and its relationships, and physical model unveils the implementation details of a data model. That's the general process how we build data models. Depending on the business needs and usage patterns, we have various data applications ranging from transactional to analytical. Now, mainly two kinds of applications that we deal with: OLTP, that is online transaction processing system, that mainly employs entity relationship models to favor business transactions. On the other hand, we have OLAP, online analytical processing, that uses analytical models to facilitate business analytics. OLTP data needs to undergo a transformation to enable business analytics. In data modeling, to enable the analytics, we usually model it dimensionally. The dimension model introduced by Ralph Kimball is a unique data structure technique optimized for enterprise data analytics. It comprises of facts from business processes and contextual information known as dimensions. Star and Snowflake schema models are widely used dimension models. And with the emergence of big data platforms, dimension models are still useful for big data modeling. Big data is often characterized by 5 V's, known as volume, velocity, variety, veracity, and value. Because of the nature of big data, we need to model it differently, and this slide presents some of the key distinctions to model big data. The traditional data model follows design first and then develop approach, while we explore big data and then analyze it. Traditional data model usage is top-down, hierarchical, and more of slicing and dicing, while big data models are used in a democratic fashion. Traditional models are more on a passive and push methods, while big data models are more collaborative. Data volume increases at a steady pace in traditional applications, while big data grows exponentially. Lastly, the main purpose is BI for traditional models, while big data models are used for statistical analysis, ML, and several other use cases. means that the way we designed data model needs a change to take advantage of the inherent architecture and distributed processing offered by Hadoop. The weaknesses are threefold when we deal with the characteristics of big data using traditional modeling. The first one is scaling cost is too high with traditional architecture, as it requires very robust and expensive specialized servers which are designed to prevent failure and data loss. Traditional modeling never meant for near real-time processing. They support well for batch processing of data. On the other hand, SQL queries can take a long time to process and execute, the range of several days as well. A Visa use case is very well known. A mission-critical query at Visa took more than a month of machine processing time. There are limitations in processing semi-structured and unstructured data with traditional techniques. Due to cheap storage, exponential data growth, and increased data demand, we ended up with these situations in enterprise data lake, which represents the current state of big data models. There are too many data models, and that's the complaint that we hear from stakeholders a lot. And often these models are repetitive. Which model should I use for my task? Why do this model show X and that model shows Y for the same matrix? Why did this model stop refreshing after March 19th, 2020? Is it related with the lockdown? My query doesn't respond when I try to join these models. These are some of the key pain points when we look at big data models in today's time. Big data modeling. While we model big data, we should still think dimensionally. Dividing the data world into facts and dimensions removes the complexity, and business users find the concept of dimensions to be more natural and easy to understand. Confirmed dimensions should be used to integrate enterprise data sources because they are the glue to hold together enterprise analytics. They will help to maintain the source of truth. The confirmed dimensions are perhaps the most powerful base practice inherited from the traditional data warehousing world. Big data models should integrate structured, semi-structured, and unstructured data sources, integrating a variety of data sources and serving insights add a significant business value. Divide and conquer with distributed and parallel processing is a really powerful principle to process a massive volume of data, and it also solves the problem of joining large fact tables. Now, how to achieve scalability with big data models? One of the best practices is to denormalize not just the data but business processes as well. Keep one model for a specific grain. Even though data comes from different business processes or business verticals, metrics with the same grain should be stored in a single model. And this is essential as joining big data are very costly. One huge fact table is definitely better than multiple large tables. This is to avoid big joins with big data models. And here's an example of a design for a medical provider who uses electronic health records practice management applications to deal with normal day-to-day operation. And from this slide on, we'll use this example to showcase the design of big data models. And consider that in traditional data modeling, we have a model tracking claim-related facts, which stores the aggregations and some of the key metrics and flags for various claims. The second is patient fact, which stores patients related fact for a provider. And the third one is appointment fact, like when the patient make an appointment, what kind of that appointment is, how long was that, and whether the patient made the appointment. All this data is stored in the appointments fact. For simplicity, we only kept these three sources for now and assuming that these are the three facts that we had using traditional modeling. Now, to turn it in a big data model, like as this principle say, one grain is equal to one model, better to have them in single model with the same grain. Like all of them, if we group them using a date and provider ID, all the metrics should be combined into a single model. Velocity was introduced with big data. For some use cases, it's better to have limited data in real time than lots of data at a low speed. Nightly processing may be an old school in big data world. NRT or real-time processing is preferable for many enterprises. How can you bring your weekly or nightly processing down to hourly or every few minutes or even a micro batches? Batches should be considered for data models as well. Here's an example that shows how daily processing can be further enhanced to process data more frequently using batches. Claim transactions are processed in a transactional table. At the same time, patient appointments are also tracked in a transactional manner. In order to model it, we had provider stats model with a batch ID that is a unit of work derived by timestamp. And both the metrics like claim return metrics and patient appointment metrics are combined into a single model, which is not processed nightly or weekly, but you can process it several times during the day. Next is for transaction models. Transaction models are useful to keep all transactions in a unified model, and that is to avoid large table scans, and intermediate results are already ready for the downstream models. For the simplicity, we are using the same examples shown in the previous slide. Claim transactions and patient appointments can be stored in a single model using complex types. This will reduce the number of joins in the downstream models and queries. The transaction model can serve as a mid-tier model that can be used by other models or directly in your queries to use transactional data. If you see here, the complex types are used to store each transaction for various transactional application. Here, for the simplicity, we only kept two, claim transaction and patient appointments. Big data model can take more time to process massive volume of data. One option is to divide processing down using iterations to speed it up. For instance, there are some life-to-date metrics which requires scanning full sources to calculate life-to-date values. In this example, number of LTD claims indicates the number of claims in the lifespan, while number of claims shows the claim count for a specific day. These LTD metrics may be from multiple sources, and that can add processing time significantly. When you have this kind of metrics in your model, the model processing can take more time. And processing them in iterations can reduce the processing time significantly. We can solve it using the iterative processing. In the first iteration, we can calculate daily metrics from multiple sources and store it in a model. In the second iteration, we can read the daily metrics as well as the last known values for LTD metrics, and we can calculate the new LTD values for that specific day. This example breaks processing down by metric types such as daily versus LTD. Iterations can also break processing down by data sources such as heavy data sources versus the smaller volume of data, or by velocity of data sources. Some sources may be available every hour, some may be available every day. So based on that, we can make different iterations. One of the important aspects is to build a data model lineage. When you start building data models, you don't realize where you will end up. With big data, you never know how big your tree will grow. Data model lineage, a part of data governance practice, helps to learn how data models are processed, and it is also useful to visualize a dependency chain. When something goes wrong, it saves a significant amount of time. It increases the usability of models by identifying duplicate insights or data models. One of the last idea is partitioning, and it is one other key criteria to achieve scalability. It is very obvious and should be used as designer's discretion. And when you choose the path of data modeling, what you should expect. The first one is performance queries. They make model usable, keep platform stable, and reduces I/O throughput. The reusability of metrics is critical as well. Big data platform doesn't have disk space constraint, but not focusing on reusability will end up in some crap models and inconsistent insights. Value addition is of utmost importance for stakeholders. Consistent metrics not only build trust, but it also reduces troubleshooting time remarkably. And this is what we should expect while scaling our models. To conclude this session, let's summarize what we have gone through. There should be a single model for the single grain, and if the grain changes, design a new model. And for the single grain, even though the data comes from various business processes or even different business verticals, it should be stored in a single model. One huge table is always better than multiple models because it will avoid join at the later stage. Transitional model should be used to merge key transactions. That will relieve pressure on downstream models and queries. Batch processing will be useful to serve insights faster than daily or weekly processing. Iterative processing should be used to divide and conquer bottlenecks. Partitioning should be used at discretion as well. And we should present data model lineage to increase usability for our data pipeline processes. And that's the end of my presentation today. Thanks for your time. And you can reach me on LinkedIn for any questions you have about my presentation. Thanks a lot.